Hello everyone. In continuation with the previous topic, we are studying the apparent weight of a man in a lift. This is also an application of the second and the third law of motion. So we have 5 cases for the apparent weight of a man in a lift. The first case is that when lift is moving up with uniform acceleration. In all these cases, some important points we need to remember that this apparent weight is given by normal reaction of the surface on the man, right? First thing this, and second thing which we need to remember in all the 5 cases is we have to use the second law of motion, that is the net force along the direction of motion is equal to mass into acceleration. So for that we need to draw the diagram of the lift where the man is here and the lift is moving up with uniform acceleration. The weight always acts downwards, yeah, and the normal reaction of the surface always acts normal to the surface on which the person or the object is there. So for writing this equation, I'll just mention that second law in this form, the way we are using the net force along motion is equal to mass into acceleration. Okay, so this gives me net force along motion is this direction. So this means R must be greater. So R minus W will give you mass of the person into acceleration. This we have to use everywhere. And now from here I need to calculate the normal reaction, that is the apparent weight. This gives me MA plus W, and this means the apparent weight in this case increases. Yeah, because this is the real weight and this is the R is the apparent weight. So this can be converted into a different form, MA plus MG. MG is the weight. So I can write it MA plus G. This is another form of the apparent weight. So this is apparent weight. This was the first case. Yeah. So then now we will discuss the second case. So for the second case, I'm taking the lift is moving down with uniform acceleration. So second case is moving down with uniform acceleration. So for that again I'll have to draw the diagram of a lift. Yes, the person in the lift, acceleration downward as the motion of the lift is downwards, and in this case the weight is acting down because it always acts down, and the normal reaction normal to the surface. Now we are using the second law, that is net force along motion is equal to mass into acceleration. Now this is moving this way, that means net force is along downward direction. So W minus R is equal to mass into acceleration, where m is the real mass of the person. Mass is generally considered constant at normal speeds. So R I have to find out because R is the apparent weight. So this gives me W minus ma. So what can we infer from here? We can infer that this apparent weight, that is normal reaction, this is less than the real weight. That means it decreases in this case. You can say that apparent weight is less than the real weight. Now for the other form, I can write this weight as mass into G minus ma. So the other form of the formula may be m into G minus a. Right? Now let's take the third case. When lift is moving down with uniform velocity. This is the third case. Now again the lift will be drawn in the same way. Yes, the person inside the lift, it is moving down with uniform velocity. What does it mean? That the acceleration is 0. Okay, m is the real mass, or you can say the mass is always real. This is the weight acting down. This is the normal reaction. How do we write the equation? Net force along motion is equal to mass into acceleration. So what will I write? W minus R, because the motion is downward, so this force we consider this way. So we'll write down W minus R is equal to m into 0. So this gives me W is equal to R. Or you can say that real weight is equal to apparent weight in this case. Okay, so therefore no change. Okay, now we are taking the fourth case, which you already understood how to go about it. The fourth case will be when the lift is moving up with uniform velocity. So I'm talking about fourth, up motion, uniform velocity, and that means the acceleration is 0. So what will be the equation? For upward motion, I'll write down the equation net force along motion is equal to mass into acceleration is 0 in this case. So from here, the apparent weight is equal to real weight. Okay, so no change in this case as well, right? Let's take the fifth case. Fifth case is when the string of the lift breaks. See, what will happen when the string will break? It will move under the effect of gravity, or you can say it is a case of free fall, or you can say that its acceleration will be equal to the acceleration due to gravity. So for that case, again we are drawing the lift. This is the person. The weight is acting down. It always acts down. Normal reaction, normal to the surface, and the string breaks. So what does that mean? The acceleration is equal to acceleration due to gravity. This is a case of free fall. Now how to write the equation? Net force along motion, it is moving down now. So for down, net force along motion will be this, is equal to mass into acceleration. How much is the acceleration, beta? G. So R will be W minus mg, and we know that W is mg. So your apparent weight comes out to be 0. Or you can say that there will be weightlessness. So this is apparent weight is equal to 0 in this case. Or you can say that it's a case of weightlessness. Okay, so this is all for this current video. Hope you have understood. There is a question, direct numerical based on this concept. So try and solve that question from NCERT. That's all for now. Thank you and have a nice day.